0.
Oh, right. Oh, yeah, it's 90, right?
It's 90 degrees.
There you go.
Yeah, because cosine of 90 is 0. And remember, I did that in class. I went and had the board down and I tilted. When I got them at 90%, what happened? It went totally black.
Okay.
So
Right?
can you explain again why putting a middle filter will allow?
That's what we're just going to do.
Oh, sorry.
All right, that's where I'm headed. So what if I put a filter in between? I'm going to go ahead. Actually, no, I'm going to make it complicated. All right. Not really. I'm going to put a filter at 30 degrees relative to the second filter and 60 degrees relative to the first filter. Are you with me? Okay. We're going to chase this through. So, how many filters have I got? 3. So, I start with the first filter. I have I naught. What makes it through onto the, so I did it backwards. What's the intensity after the first filter? Okay, so we know it's 1/2 I naught simply because by average cosine is 1/2. That's the first filter. And now which direction is it polarized? Since this is my first filter.
Second one.
It's polarized vertically, right? Because my theta 1 is here. Now I know it's polarized vertically. So this becomes the intensity for the second. So for the second filter, it's equal to I naught, which is 1/2 I naught, because that's what hits the second filter, isn't it? What's the angle between the polarized light and the second filter, which is the one here in the middle? 60, right? So I get cosine squared 60, all right? And that should be what? Yeah, go
Can
ahead.
you explain that whole step over for the second one?
Right. So this is the intensity from the first filter. That's come down, it's my intensity. So the law is intensity times cosine squared of the angle. So I just bring this answer down and put it here. Then the angle between this and the next thing it hits is 60 degrees, so I have cosine squared 60. All right. Cosine of 60 is root 3 over 2. No, cosine squared of 60. Cosine squared of 60 is 3/4.
Sine, cosine 60 is half.
Cosine of 60 is square root of 2 over 2. Oh, I'm doing sine of 60. Yeah, I'll wake up. All right. Yes. Oh, so cosine 60 is 1/2, isn't it? All right. So then when I square 1/2, I get 1/4. All right. Sorry, that was my bad there for a second. So this just gives me equals 1/8 I naught. So that's the second one. That's how much makes it through the second one. All right. On the third one, this is the one I was doing in my head, by the way. I still don't excuse. This is my initial intensity
Cosine squared 30.
because it's the one that makes it to the third filter. What's the angle between the polarization and the final filter? 30. So now it's cosine squared of 30, and this is where I get my square root of 3 over 2, giving me 3/4. All right, and so I get 3/24 I naught. And you don't have to do fractions, you can do the ugly decimals your calculator will give you. I'm still stuck in the 1960s. Yeah.
So is this what we might do for the test?
This is the kind of thing you could do, right, where I would have something like this. So it's a very straightforward application of the law of malice. I would give you very clear geometry, but if you understand this, you'll understand anything that I would do. So do you understand this, and if not, now's a good time to say no. Yes?
Isn't that 1 over 8?
Yeah, I've got 1/8 times 3/4. Did I do something wrong, 32?
Oh.
I did do something wrong, I just can't do math. Yeah.
So when doing a problem like this, we'll just go ahead and be like, okay, so in the first one this happens, and then now that I becomes the I initial for the second one.
Exactly. It's just a chain thing, that once it goes through one filter, that intensity is the initial intensity for the next filter, which is then the initial intensity for the next filter.
But you're gonna let us know which one's the initial, right?
I have to. I mean, so that's why I labeled this as 1 and 2. But then when I said I put one in between them.
Right.
So the thing that we want to see, don't lose that. The thing that I want you to first see is if I don't have this filter there,
We can still.
we get nothing.
Yeah.
When I slide that filter in, it's not a lot, but I get something. And that's why. Because when I put that filter in, the light still passes through that filter because it's not at 90-degree angles. That means I have light, which also hits something else which is not at 90 degrees, so it actually can get through.
Oh, gotcha. So if the first filter is lined vertically and you have light passing through it, then only vertical rays and rays that have a vertical component will pass through, right?
Correct.
So then that means that when it does pass through this filter,
Now it's oriented that way.
okay. So do the rays Okay, so I'm getting, so you're just gonna get the rays that have a line and an X?
Let's take a look at this. So when they come through, we have electric field is pointing this way, and this is the axis of my next filter.
Okay,
Is there a component of this vector that's along this? Yeah, that's why it goes through.
okay,
Right, so this amount goes this way, this part cancels entirely.
okay, so you're just gonna have the one.
So
go through
this is the thing, it's vectors, and vectors are always squirrely like this.
So then when you get to the third polarizer, it's horizontal completely.
Yes.
So how does that go through?
Oh, because the same thing happens. Once I get here, so now it's polarized this way, which has a component that's horizontal. I'm sorry, I totally forgot.
No, that's fine, okay. So first, second, third stand for the filters that you're putting in, right? All right, so like you said, that the last one's going to be completely horizontal.
Exactly.
But why is it, well, how did we get the degree to be 30?
Oh, so this is what this is first, second, third. So when I go through here, it's polarized this way, and when I hit this filter, there is a component of this that's in that direction. So now I get a much dimmer light. It's in fact reduced by 1/8, to 1/8, not it's reduced by 7/8,
Okay.
right? But it's this way. And now there's a component of this that's in this direction. So it's reduced again, but some does get through. If I could put perfect polarizers where I have one here and then basically an infinite number where each one is just tilted a little bit, most of the light comes through out the other end, but at a completely different polarization. It's one of the curious things about polarization. And nature sometimes does that, causing what, this is way more than you need, but nature does that so that in certain solutions, certain sugars and stuff, you shoot light through, it actually circularly polarizes it so that it's actually, the field ends up spinning in circles because it's a gradual shift as it goes through.
Okay.
But, yeah, what was your question?
Oh, okay, so just to confirm, so the first time, the first filter, you're gonna have half of it, right?
Because, yes, unpolarized by going through a filter, will only half makes it.
And then the second time, you have to do,
The cosine of the angle between the first filter and the second filter. So if I look at my 1 and 2, there's a 60-degree angle, so I get the 1/2 that made it times the cosine squared of that angle between them.
and then.
Now that's my new one, which is 1/8, and that becomes the initial for the third one.
And then you do the angle between the second one and the third.
Right, because it's
Okay.
stupid, it doesn't remember there was anything else, and it only sees the new one it's going.
Okay, thank you.
All right, I guess you're next.
Okay, so I'm getting a little confused because I know that if you have a polarizer that's vertical and you have light going through it, then it's only gonna have light that goes in that direction. So then if we don't have that filter in the middle, it's zero, right? Because
Because the next one's 90 degrees away, so there's no part of this that lies in this direction.
But then my question is, if you have now the filter in the middle, and now you're having components that do have a Y component, why didn't we have that with just the horizontal?
Because it's one of the weird things of geometry is that when it's 90 degrees, there's no part of this that's in this. But when I have any angle, suddenly, and it's because it's vectors, not pure numbers,
Okay.
right? So that once I've twisted it, I now have a component in the new direction.
So it was always there, but when you just...
No, it wasn't there. It wasn't there till I hit the second filter. The mechanism of this has to do with how the light interacts with the long chains of polymers that are in the polarizing.
Okay.
And so they actually act like antennas, so they rebroadcast it in a new direction. But I think you're might be overthinking it. So if this is my first one,
Yeah.
no part of this moves in this direction.
Yeah.
But as a vector, if I look at it like this, there's this amount of this direction and there's this amount of this direction.
Okay.
This part makes it. Now once it makes it, this isn't going to cancel it because now there's this amount in that direction and this amount that's perpendicular. This part would get canceled, this part would make it. So it's true. Putting the extra filter in made something happen that didn't happen before. All right. So yeah, it's very bizarre. Any other questions on this before we move on? And please don't. I'll just move on because there's other stuff to talk about, but this is more important for right now. If you've got questions on it at all.
Filter in front or behind the two filters? Like
If I were to take this out and put it in the front, how much would we make it through? None. Because although it would make it through this filter and the first filter here, at that point it would be vertically polarized, and when it hit the second one this way, it would anytime there's a 90-degree angle between two filters, it kills it, no matter what happens before or after. So putting this filter in front or all the way behind would not help. In fact, remember, that's what I showed. Maybe we should have done this first. But I had the two filters like this, and when I slid it into the side, we could see through it. But if I put it in the front or I put it in the back, we couldn't see. But it was only when I put it between the two filters we could see. Because that's what turns it.
Can you bring those on Friday?
Yes, we can bring those back. All right. So, in my book, this is basically a wrap. All right, we've covered everything there is in optics. You know everything there is to know. You could go get jobs in optics at this point. So, what's the test actually going to consist of? So, how do we start the semester? We start the semester with Snell's law and the law of reflection. So, guess what? There aren't a lot of direct questions that I can use the law of reflection on, but we still need to know. So, what's the law of reflection?
Incidence angle.
Theta 1 equals theta 2, or angle of incidence equals angle of reflection, right? It's just that simple. And,
With normal.
oh, yes. Just, you know, when people who come late, they... All right, yes.
What?
I'll give you 2, just to make up for it. Actually, 3. Anybody else? All right, so law of reflection, you understand theta 1 equals theta 2. Then we have the law of refraction, which is what? N1 sine theta 1 equals N2 sine theta 2. All right, that's the law of refraction, Snell's law. All right, so we'll get back. In the order that I kind of put the test together, number 1, which is daunting, is more than you need to know, but if you know number 1, you're ready for anything I can throw at you. So basically, there are six conditions that we need to know how to draw ray diagrams for. A converging mirror with an object outside the focal point, a converging mirror with the object inside the focal point, and a diverging mirror. And then for lenses, the same 3. A converging lens, object outside the focal point, converging lens, object inside the focal point, and a diverging lens. But the laws for drawing the rays are different. So I'm going to go over that briefly right now. We may not make it through this today. That's what Friday's for. Okay. I'm going to be a little bit careless on the board, but I'm going to give you rulers, and I highly, highly recommend that you practice drawing ray diagrams with rulers. Right? So basically, how I do this is I put my mirror or my lens here as a straight line. I then sketch what I'm going to be using around it, but I don't draw my lines so that I draw my lines to my straight line. Okay? So I'm doing a converging mirror, which is concave. I remind you it's concave, so I'll just kind of do that to remind you that's a converging mirror, and I'm putting the object on this side. Are we good with that? I'm going to say that I have a focal point that's right here, and I said the first one we're going to do outside the focal point, so I'm going to start here. And again, guys, I'm just going to sketch, but help me. What's the first ray that you remember I told you to draw?
Parallel.
In parallel out through the focal point. So we come in parallel, and we come out through the focal point. Does that make sense? Notice that I went to the line, not to the mirror. Right? Because we treat the mirrors as flat. They're curved, but they're a very tiny curvature, so we treat them as flat. Anybody got any question about that line? What's the next? Go ahead.
What kind of mirror is it?
It's a concave, so curved like that. All right, so it's also a converging mirror, is what we call it. All right, what's the next line?
Focal point.
If I go through the focal point, it should do what?
Not parallel.
All right. Notice you don't have to do this, but when you're using all one color, if you have colored pencils or pens and would like to bring them to the test, yay you. It'll make this easier. But if you don't, one of the things I do is I'll put little arrows, like one arrow here, to indicate which ray is going on. 2, 2, and 2 to show me that it's which ray is what's doing. So when if all things are fair, and I haven't quite done this right, but this is where the image up to form, right? But let's just do one more to test it. What's the third one? The book gives you that one about center of curvature. I'm not going to use it. I'm just going to say, look, if I have a mirror that's curved like this, and I'm on the axis, if any light hits this point right here, does it make sense to you, if I've done that right, this part of the mirror is essentially flat. I mean, it's normal to so whatever goes in comes out at exactly the same angle. So how I do that, guys, is I take this and I put it down below, and I would say, okay, I come here, I come there, and you know, it doesn't, I clearly get this all lined up right. If I had a ruler, it would work, but the basic thing is I have those three rays. Where they supposedly intersect, which is kind of all over the map, is going to give me my image. When you draw these, if they don't intersect all at one point, do you lose points? No, not if it's reasonable. If they're completely intersecting wrong because you drew them wrong, yes. But if you've drawn them right and they don't even intersect in exactly the same place, do not waste time there. There's other good stuff to do on the test. As long as it's approximately right, I'm going to go with it. All right? Know how to draw it, but I'm not going to penalize you for being off a few millimeters here and there.
Will you please go back to the center of curvature idea?
Yes, so if I'm doing this, if I have this as my object, no matter how I've got it, what happens is if it hits the center, by geometry, if it hits here, it has to come back to exactly the same shape below it. They have to be the exact same, congruent triangles, right? And so that's the way I draw that third ray. Anybody have any questions on those? Yes?
Okay.
All right. So based on this picture, did this produce a real or a virtual image? Real because that's really light. Those rays really, that's really light. Light really went there, that makes a real image. I can put that on a piece of paper. Are you good with that? Okay. What can you tell me about the magnification? Anything? Based on that picture, it's pretty close to what? It's pretty close to 1. Right? It's almost the same size as the object. So if you get 1.7 and your picture looks like that, something's wrong. Do you understand what I'm saying? So from your picture, it looks like they cross pretty close. You know, I mean, it should be about the same size. If I draw it more carefully, we'd see that. So we know that it's real. We know that the magnification is on the order of 1. So 0.8, 1.2, we believe those kinds of answers. But if we've got a 3 from calculating it, then my picture's got to be wrong.
So when we have numbers,
But, I mean, so
you give us focal point and
yeah, right. And so here's the thing: I would give you focal points. I would give you an object of a certain size, and I would tell you to sketch it, and then you'll look and see if those numbers make sense. So the way it's going to go, you're going to have numbers. You're going to calculate it using the equation. You're going to calculate it using the picture, and the picture and the equation better give similarly looking answers. Yeah.
A different question. I understand here, the focal point is positive because light is coming in here. The focal distance
The focal point is what?
should be positive, right?
Why do I know the focal point is positive? I do know that. How do I know that?
Because light will meet there.
Because it's on the side where light is.
Okay, that's okay.
All right. For a mirror, if light can go to the focal point, that makes it real.
Yes.
If the focal point were on this side, light can never get to that side of the mirror. That makes it virtual. But if the focal point's on the same side where light is, that makes it real.
Okay.
Now, or where light goes. So if I hit a mirror, and guys, don't make this hard. If I hit a mirror, here's the mirror, here's the light. Where's the light? Which side can the light go to? Only here.
Only here.
That makes this the real side. If I hit a mirror and the image forms there, light can't go there. That makes it virtual. On a lens, that may not be quite as obvious. Well, actually it is. All right, so I have an arrow. I'm going to have light come in. It's going to hit this lens. If it forms an image over here, which it won't with this particular thing, but who cares? If it formed an image here, there's really light on that side. Does that make it real? No, because it's where does the light go? All right, and the light goes through. So after it hits this lens, it's on this side. It's not going back there. So that makes this the real side of the lens. This is the real side of a mirror because they do different things. Lenses transmit light, mirrors reflect light. So this coming in, it's a real image if the image forms on this side. It's a virtual image if the image forms on this side because, listen to me, since light is on this side, if an image forms here, the only way it could be real is if it were psychic light. because it would need to form an image before it ever knew there was a lens. Do you understand what I'm saying? If the image is going to form here, and it's real, which means light goes through the image, it has to go there before it gets here, and that's not going to happen. Only Miss Cleo can do that. That's what you got.
And that's for the convex lens.
So this is the real side,
You got
if
it.
the light's coming from this way. If the light were going this way, I mean, so lenses transmit light, the real side is where it goes after hitting the lens. Mirrors reflect light, the real side is where light goes after hitting the mirror. Okay? All right, so then we're going to repeat the experiment, but we're going to use a mirror, and we're going to go inside the focal point because concave mirrors can do two things. So again, I've got this going on. I've got the focal point here, and I've got my object here. All right, well, I'm not going to do that. All right, so the rules remain the same, but they get a little tricky. Light that comes in parallel does what? Okay, it goes through the focal point. Okay. Light that goes through the focal point comes out parallel, but that's not possible because if light goes through the focal point, it ain't coming back. So we get a little tricky here. We say, pretend as though it had come from the focal point. You get it? So it's aiming from the focal point, but it doesn't start there. It starts at the object. Does everybody understand what I just did there? My focal point's here. If I draw a line from the focal point to the tip of my arrow, if light comes from that angle, then it's going to come out parallel. And I'll show you why. Because if light had come in this direction, where would it go? Through the focal point.
Yes.
So we just reverse that ray and go the other direction.
Good.
That's tricky. That's why I'm pointing it out. So for the second one, you kind of do a little dotted line from the focal point to the tip of the arrow and keep going to the mirror and then come out parallel. All right? Then the third one is just the same as it was before, which is just make anything that hits the middle comes back out. I did that really badly, but whatever. Right, so there we go. And these are not coming together. These three rays are not coming together. They're spreading apart. So what they do is they look as though they're coming from the other side. So I extend these rays back to this side and they intersect on this side. Do you get it? We draw the three rays. The one that comes in parallel goes through the focal point. The one that comes from the focal point goes out parallel. The one that reflects in the middle comes out at exactly the same angle that it went in. They're diverging. They're not going to meet. But they look as though they met on the other side of the mirror when I extend them back with dotted line, saying this makes a virtual image behind the mirror. Did we see anything like this in lab? Yes, because remember what I had you do is I had you take that concave mirror and hold it really close to your eye, and what did you see? A really big eye that was right side up, which you know immediately means that it is virtual. The image formed on the other side. Are we good? So that's the two versions that we have for concave mirror. Yes?
Image would be bigger.
Yes, because here's my object, here's my image. Ooh, well, quite a bit bigger. It's not always going to be bigger, but if it is bigger, it's going to be with a concave or a converging mirror lens. Diverging mirror lenses always make images that are smaller. All right, and I'm going to do that in just a second. So I'm going to erase here. Did you have a question?
Virtual, right?
Yes. How do you know? Because what happens, this is a mirror, and the image is here, so light can't get to that side of the mirror.
Do I need to know how to say it exactly like that?
You need to say it in a way that I can understand.
Because I know.
So in this case, magnification would be greater than 1?
Yes. It would be, we would have a positive greater than 1 magnification. On that one that I erased, we would have a negative, and it could have been a little bigger than 1, but not much. We would have been close to 1. Yeah.
You say you would give us numbers like, can
Yeah, and the problem, what I'll say is this is the height of the arrow, it's 15 centimeters, or I won't do that. How about 2 centimeters tall, and it's 15 centimeters in front of the mirror, blah, blah, I would give you all the numbers. So what you could do, and what I would recommend doing, is first just do the math from the equation. And help that guide you in your picture if you're not sure how your picture ought to go. I mean, use what you know. I mean, if you're using an equation that you know to figure out what the right answers are, I'm okay with that. But you've got to make it look like you knew how to draw the picture. Once you realize where it needs to go, then draw it in a way that makes it look like you knew what to do. Fake me out a little. All right. So next we're going to do a convex mirror. And the focal point is where? I'm a convex, so it's over here, right? How do I know on a mirror where to put the focal point? Look for the center of curvature, and then it's half of that. So where, if I've got a round thing, where's the center of that circle? On that side, therefore my focal point's on that side. All right? No. If I were going to make this a big circle, where's the center of that circle? Right? Okay, so let me put focal point here. All right, put the arrow here. All right, so first things first, we draw the horizontal line in, and now what do I do? I can't go to the focal point.
Imagine it.
But so I come as though I'd come from the focal point. So I draw a little dotted line here, and it reflects away from it. Does that make sense to everybody? So it comes in parallel, and I can't go to that point because it's on the wrong side of the mirror, so I reflect away from that focal point. This is why it's called a diverging mirror, because now the ray has diverged from the horizontal, where, well, actually, I erased the one that I needed. So converging tends to bend towards. All right, what's the next ray I want to draw? Aim for the focal point, right? So I aim for the focal point, but I'm not going to get there, and instead it's going to come out horizontal. Do you see it? So you aim for the focal point, but you hit the mirror, and the mirror reflects it out parallel. And what's the last one? I take this, and I say whatever hits the middle comes back out at the same angle. All right, because that's getting a little hard to see, I'm going to make the reflected rays a different color. I don't know if that different color actually helps. Can you actually see the 3 yellow rays? Okay. So I extend these back. So extend, extend, extend. Can you all see this ray extended back, this ray extended back, and this ray extended? They cross a single point. And that place where all 3 rays cross is where the image forms. Are you good with that?
It's going to be, light doesn't go back, right?
It doesn't. So
I don't know.
real means really there. You can put it on paper. And if it didn't really go there, then it must be virtual.
And that's why it's going to be upside
It's going to be what? It's going to be right side up. Remember, virtual images are the only ones that are right side up. Real images are always upside down.
It's not. The real images are upside down, and then virtual are
Right side up. Okay. So not only is it virtual, what can you tell me about the magnification? It's small. All right. And what I want you to be able to do, I want you to be able to explain that based on the equation. So here's the thing. If it's going to be a convex mirror, the focal length is negative, isn't it? This is negative. This is always positive, right? The object is always real. Right? Objects are real. So it's going to always be real. That makes it positive. We know the focal length is negative because it's on the side of the mirror where light doesn't go. From this information, mathematically speaking, what do I have to add to a positive number to get a negative number? It has to be negative, right? Do you see it? This has to be negative. That means that the image is going to form on the virtual side. But more than that, Which is bigger, 1 over s or 1 over s prime? This has got to be bigger or it wouldn't go negative. So this is bigger. But that means that s is bigger than s prime. Because those are upside down. Do you follow that? Let's go here again. In order for two numbers to add up negative, this one has to be more negative than this is positive. So this has to be a bigger, I should do this actually. The absolute value of this has to be bigger than the absolute value of that. Right? So that when I subtract it, I get a negative number. But if I have 1/2, is 1/2 bigger or smaller than 1/4? If you got half of something, you got a fourth of something, which one is more? 1/2. If I invert them, is 4 bigger than 2? So exactly what happens is when you've got fractions, when you invert them, the inequality goes the other way. So that means that s is actually bigger than s prime. Are we good? And again, I'm talking absolute values. I need to be careful with that. Okay, magnification is defined to be minus s prime over s. So let's think, is s ever negative? No. Is s prime negative in this case?
Yes.
Yes. So a negative makes a, so I get a positive magnification, which means the image should be straight up, upright, not upside down, and it is. But I just told you that s is always bigger than s prime. What does that tell you about the size? Always smaller. S prime is a larger number. S is bigger than s prime. 1 over s prime is bigger than 1 over s, but s is bigger than 1 over s. Is bigger than s prime. All right, and that tells me the image is always going to be smaller. I can never enlarge an image with a concave mirror. Convex mirror. I'll wake up. That's the standard thing I told you every time on your car, on the side mirrors, when they say images may be larger than they appear, it's because they always use a convex mirror. It always makes the images smaller. And our brain, seeing a car, knows the idea of a car, how big it is, and so when we see this tiny car, we assume that means it's far. That's how we interpret size. So that's why that illusion happens, because we already know the size of a car. Who's it? Sorry.
So in case of flat mirror, how
In case of which?
flat mirror?
Okay.
Would you consider it a larger convex, larger concave? Just a flat mirror?
Flat mirrors, here's the beautiful thing about flat mirrors. The image of a flat mirror is always exactly the same size as the object. Okay? Why is that? Because the focal length is infinite.
Infinite, that becomes 0. Yeah.
All right? And so 1 over f is 0. And so we have 1 over s plus 1 over s prime equals 0. So they have to be exactly equal, but 1 is negative, and that's what happens. S prime is negative of the exact value of s. Give me I'm the same size, but I'm virtual. All right? So, yeah, go ahead.
So for cars that use the convex mirrors, right?
Yeah, and mom and pop grocery stores that have the little mirror up in the corner where they can see the whole shop, those are also convex because you wouldn't really want that mirror to invert the image, would you? And concave mirrors invert images. And people upside down, it's hard to interpret. So we have the convex mirror, it lets them see, but it also means that everything looks smaller. All of it. A convex mirror will always make things look smaller. So far, so good? Your head's full yet? The good news is that we're only 1 tiny tenth of the way through. No. This takes time, and there's really no way for me to help you practice this. If you don't practice it, you're going to screw it. It's just that simple. Once you practice enough, it's obvious. It'll take no time at all to do it right if you practice it. Don't practice.